All right, hi there, guys. My name is Wilfrid, and I'm a senior math tutor. And today I'll be covering 9 questions related to algebra, functions, and calculus. A little bit backstory upon myself: I graduated with McMaster with a major in biochemistry and a minor in mathematics. And if you have any other issues with your math homework or your chemistry homework or any questions related to any kind of concepts related to math or chemistry, just submit them through OneClass and we'll get to them as soon as possible. But other than that, let's jump right into it. Okay, so the first question reads, using the arc length formula, find the length of the curve y equals 2x minus 5 in the interval of -1 to 3. And then check your answer by noting that the curve is a line segment and calculating its length by distance formula. So the first thing is that we have our function here, which is y equals 2x minus 5. So we do note that this is a linear equation. So this refers to a line on a graph. And that means that we can use the distance formula to calculate the distance of this line in the interval of -1 to 3. Okay? And it's a closed interval. So the distance formula that we are using is d equals basically x2 squared, sorry, y2 squared minus y1 squared. Okay. So this formula is x2 minus x1 squared plus y2 minus y1 squared. Okay. So that's the distance formula. And using the arc length formula, gives us the length of a curve by calculating the definite integral from 3 to 1 of the square root of 1 plus the derivative of our function squared. Okay, so we're going to use the arc length formula and the distance formula to calculate the length of the curve, and if these two are right, then we can verify that the arc length formula is indeed working or is correct. Okay, so the first thing that we want to do here is to find the derivative of our function, which is our curve, which is 2x minus 5. So dy over dx is basically 2, right? Because the derivative of 2x is 2. All right. So now using the arc length formula, we'll label it L, and I'll put L here too, just not to make it confusing. Okay. So the length is equal to the definite integral of the square root of 1 plus the derivative of our function squared. Okay. So in this case, our derivative of our function is 2. So 1 plus 2 squared dx. And that's equal to, it's 3 negative 1, my bad. And that's equal to the root of 5x from 3 to -1. So calculating that, we get the root of 5 times 3 minus negative root 5, which equals 4 times root 5. Okay? So that's using the arc length formula. All right? Now we're going to use the distance formula, which states that the x2 minus x1 squared plus y2 minus y1. So we have to find y2 and x2 first, and y1 and x1, okay? So first we're going to need to find, so if we use the second method here, we're going to need to find x1 and y1. So x1 is -1, and y1 is going to equal 2 times -1 minus 5, okay? And that is equal to -7, right? So that means x1, y1 is equal to -1, -7. And x2, y2 is going to be, so x2 is equal to 3, and y2 is equal to 2 times 3 minus 5, and that's equal to 1. So x2, y2 is 3 and 1. And now using the distance formula here, we have d is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, so if we equate these together, we get 3 minus 1 squared plus 1 minus 7 squared, and that's all square rooted here. Okay, let me just move this square to the other side. All right, and if we calculate that, what do we get here? We get 4 squared plus 8 squared square root. That's equal to the root of 80, and its radical form is basically 4 root 5. Okay, so the distance formula for our length of our curve here is the same as using the arc length formula, which gave us the same answer. So that means that the given curve is a straight line and its length is 4 root 5. So 2 more important things to note. When you're calculating the arc length of a curve, you need to make sure that you have a definite boundary for your curve. So here we have -1 to 3. And the other thing is that you need to make sure that your derivative is continuous and that it exists. If your derivative doesn't exist at that point, then you can't calculate the arc length of your curve. But other than that, this solution is correct, and we can move on. Cool. All right, so we're going to move on to the next question. So the next question reads, convert the point on the graph from rectangular to polar coordinates, with r greater than 0 and theta being from 0 to 2 pi. Okay, so in previous lessons I covered how to convert a point in Cartesian plane to the polar coordinates, and these are the 2 formulas that you have. So let's say that we have a point xy and we want to convert it to r theta. Then we use these resultant formulas to do so. So r is going to be equal to the square root of x squared plus y squared, and theta is going to be equal to the tan inverse of y over x. Okay, and these have to do with the Pythagorean identity and with the trigonometric functions. So that's how we find r and theta. And to go back, we can also use the formulas x is equal to r cos theta and y is equal to r sine theta. Okay, so you can use these formulas to go back to your rectangular coordinates. Yeah, so given the point on this graph here, Q, we have to convert this point to its polar coordinates. Okay, first we have to identify what Q is. So Q, the coordinates of Q in rectangular form is 0 and -3. Okay, so that means r is equal to the square root of 0 squared plus -3 squared. Okay, that's equal to root of 9 or 3. Okay, so theta is equal to the tan inverse of -3 over 0, or y over x. That's equal to the tan inverse of -infinity, and this this resultant is that it's equal to -90 degrees, or 3 pi over 2. Okay. So therefore, the polar coordinates are 3 and 3 pi over 2. Okay, so that's how you convert from rectangular to polar coordinates, given this specific point. Okay. So this solution is correct. Nice job. Okay, cool. So the next question reads, how do you find the absolute maximum and minimum of a function? So when we're calculating absolute maximum and minimum of a function, we have to be worried of a few things. So the first thing is that we need to make sure that our function is within a closed interval. And this is because that many functions have the absolute maximum and or absolute minimum, which is infinity or negative infinity. So if you were to include the whole set of real numbers, we will be considering the absolute max or the absolute min to be infinity or negative infinity. That's a lot of different functions already. The second thing is that we need to make sure that our function is continuous within the bounds, and that is because if the function is not continuous within our interval, then there's no point in calculating the absolute max or absolute minimum because it might not even exist in those intervals. So that's the two things that we need to note of. But here's a general algorithm or formula of how finding the absolute min and absolute max of a function. So the first thing is that we need to find the critical numbers within the interval. So that means that we need to solve for the derivative of our function. And by doing so, we have to set our derivative to equal to 0 and find the values of x that satisfy our derivative to be equal to 0. Okay? Once we find all the critical numbers of interest, then we plug in those critical numbers from step 1 and the endpoints, and we evaluate it into our original functions to find the y values of those critical points and the end points of our interval. And by doing so, we're able to identify the largest y value and the smallest y value to be our absolute max and absolute min respectively. Okay, so first let me draw out the rationale of why finding the critical numbers are very important. Okay, so here, let's say that we have a function here, and I'm just going to make it a parabola. Okay, so we have a function here, and it's a parabola. Okay, and let's say that we want to examine the function and its absolute maxes and absolute mins in the interval from this area, I guess from 1 to like 4. Okay, so we want to evaluate our parabola from 1 to 4. Okay, these are just random intervals, okay? So when we're evaluating it, right, we could either look at our function itself and visually identify where our absolute max and absolute min are, right? So the absolute max at this point here would be like our endpoints, right? Our endpoints would be like here, I guess, and like here. Okay, let's say our endpoints end up here, right? So if I were to draw a dotted line up, it would like end up here. And so these are absolute maxes, right? So I'm going to just label this as such. So these are what we call the absolute max. And we find that because we evaluate the endpoints of our function. Okay? So what about absolute min? The absolute min will be here, right? If we were to visually identify this as our absolute min. Okay? And when I talk about absolute max and talk about absolute min, I'm talking about within the closed interval that we specified. Okay? So now that we have identified these points, what is really convenient about the absolute min is that the tangent line at this point is equal to 0. And there's a theorem in calculus, and there's actually this theorem is pretty popular, which states that the critical points of the first derivative of a function relates to either a max, a min, or a saddle point. So using this information, this is why it's very important for us to calculate the critical points of a derivative. By calculating the critical points of a derivative, we're able to identify points of interest that might relate to our max, min, or a saddle point, right? And there's a second derivative test that we can use instead of plugging it into our function that will be able to allow us to identify what the max or min is of our critical points of our first derivative. However, in this algorithm here, we simply have to identify our critical points or our points of interest and then plug them in and evaluate which one is the highest value and which one is the lowest value. The final thing that I want to note is that we evaluate the endpoints of our closed interval because the derivative cannot calculate the tangent line at this point. And this is simply because of the fact that it might not accurately reflect the whole function in itself. So that's why we calculate the endpoints separately and don't use the derivative to calculate the endpoints in that sense. because the endpoints might be the absolute max or absolute min, but it might not have a tangent line with a slope of 0. So with that in mind, we're going to use an example to just clarify everything. So the example here gives us the function f of x is equal to x cubed minus 3x squared plus 1 into interval of x of -3 and 5. Okay? So the first thing that we want to do is we want to evaluate what f prime of x is. So f prime of x, if we derive this, is going to be 3x squared minus 6x. Okay? Now that we have derived it, we want to set f prime of x to be equal to 0. So we've set it to equal to 0. We have 3x squared, 3x squared minus 6x equals 0. And we're going to find the critical points. So we're going to factor out 3x here, and we're going to have x minus 2 equals 0. And we're going to solve for the values of x that make it equal 0. And the two values of x that makes this equation equal 0 is x equals 0 and x equals 2. Okay, so now our critical points and our endpoints that we want to evaluate are 0 to -3 and 5. So we want to evaluate each of these points and see which one is our absolute max and absolute min. Okay. So let's evaluate f of -3 first, and that's going to be equal to -27 minus 3 times 9 plus 1. That's equal to -27 minus -27, -53. Okay. Next, we want to evaluate f of 0. And that's going to be equal to 0 minus 0 plus 1. And that's equal to 1. Next, we want to evaluate f of 2, which is equal to 8 minus 12. Yep. Plus 1. And that's equal to -4, -3. And finally, we want to evaluate f of 5, which is the other endpoint, and that's going to equal to 125 minus 75 plus 1. So 51. Okay. Make sure I evaluate all our points here. Okay, sure. Nice. So once that we evaluate all the points, now we can label which ones are absolute max and absolute min. So our absolute min is the point f of -3, or so f of -3 and -53 is the absolute min. And 5 and 51 is the absolute max. Okay, so in this case, it ended up being that the endpoints were the min and maxes of our function, but this is not always the case. Sometimes your critical points indeed actually end up to be your absolute max and absolute min. But in this case, our endpoints ended up to be the min and max. So the solution is correct. Good work. And if you want to delve deeper, you guys can search up the second derivative test and how it relates to absolute max and absolute min. It's another way of calculating and finding where your absolute max and absolute min lies. All right, so the next question reads to ask us to simplify the given logarithmic expression. It's not in the actual question here. I believe the text was, I guess, blanked out, but the expression is 8 times log base of 3x minus 2 times log base of 3z minus 7 times log of base 3y. Okay, so we're going to use a few properties of logarithmic functions to help us calculate or to simplify this expression. The first one is the power rule of logarithms. Okay, so the power rule of logarithms states that log base of b with argument x to the power of n is also equivalent to n times log base of b with argument x. Okay, so this rule basically states that we can take the exponent of the argument and move it down to be a constant, to be a product of the log b of x. Okay, so that's the first expression. All right, what's the second one? The second one is the sum rule of logarithms, which states that log base of b of, let's say, xy can also be written as log base of b times x of x and plus log base b of y. Okay, So the third one is going to be the quotient rule, or the difference rule, which states the log base of b of x divided by y is also equal to the log base of b of x minus the log base of b of y. So we're going to use all three of these properties to help us simplify this expression. So let's write our expression again. So we have 8 of the log base of 3 of x minus 2 of the log base 3 of z minus 7 of the log base 3 of y. Okay, so the first thing we're going to do is we're going to use the power rule. We're going to take all the constants multiplying our logarithmic expressions here and move it up to be the exponents. So we're going to say this, the log base of 3 of x to the power of 8 minus log base of 3 of z squared minus log base of 3y to the power of 7. So next thing we're going to do is we're going to factor out the negative in our last two terms. So we have log base of 3z squared minus the log base, or plus the log base of 3y to the power of 7. And by doing so, we can use the sum rule to rewrite this as log base of 3 of 7 squared times y to the power of 7. Finally, we're going to use our difference rule, and we're going to simplify it to be log base of 3 of x of 8 divided by 7 z squared times y to the power of 7. And this is our simplified expression. Okay? So we use all three of these properties to simplify our expression, and this is much easier to calculate than calculating this. Okay? So this solution is correct. Nice job. Cool. All right, let's move on to question number 5 today. All right, so question number 5 reads, what is the discriminant of the quadratic function negative x squared plus 4x minus 2? Okay, so the discriminant is based off the quadratic formula, and it helps us to describe and to ascertain how many zeros the quadratic function has. Okay, so if we were to write out the quadratic formula, it will be x equals negative b plus or minus the square root of b squared minus 4ac divided by 2a. Okay, so the discriminant is based off this, and we take the terms that are within the square root. So we're going to write d as the discriminant, and it's going to be equal to b squared minus 4ac. So the value of b will the value of d will give us information about the quadratic function's solutions. Okay, so if d is greater than 0, there are 2 real solutions. Okay. If d is equal to 0, there is 1 real solution. And if d is less than 0, there are 2 imaginary solutions. Or I should say complex solutions, sorry. Okay? So, in this case, we're going to calculate the discriminant of our above function here, and it'll give us information about its solutions. Okay, so our function here is negative x squared plus 4x minus 2. So the discriminant formula is b squared minus 4ac. And we plug in b, a, and c, which is the coefficients of our standard form of our quadratic function. This is what we get. D equals 4 squared minus 4 times negative 1 times 2, and we get 16 plus 8, okay, which is equal to 24. Right? So since d is greater than 0, we know that f of x has 2 real solutions. So the discriminant helps us to know how many solutions there are, but it does not give us the magnitude or the value of these solutions itself. And to do that, you'll have to either factor it or use a quadratic formula to find it. So another way that you can think about the discriminant is its relation to the quadratic formula and how the quadratic formula works, right? So if your discriminant is greater than 0, we see here that the square root is positive, and this plus or minus function here, or this plus or minus operation here, works. What I mean by works is that you have a solution where it's negative b plus the square root of whatever, and also you have negative b minus the square root of whatever. So you have two solutions to this formula. So the discriminant is equal to 0. The square root itself is just the square root of 0, which is 0. So you're adding or subtracting from basically 0. So this operation is made null. It's made void. So by doing that, you know that there's only one real solution to this formula, which corresponds to a quadratic function. Finally, if your discriminant is less than 0, we have the square root to be of a negative number, and you know that the square root of a negative number never presents itself as a real value. Instead, we have what we call imaginary numbers or complex values to basically take part in the square root of negative numbers. So when you have a square root of a negative number, you can expect that you have two complex roots or complex solutions to your quadratic function because of the discriminant being less than 0. Okay, so that's another way that you guys can think about the discriminant and how it relates to the quadratic function zeros and how it relates to the quadratic formula. But other than that, the solution is correct and we can move on. Okay. So give me a minute. I'm just going to go to the washroom. Okay, I'm back. That was a quick washroom, but anywho. So the next question reads, use the properties of limits to find the indicated limit, basically. So the junior tutor goes on to write and to apply the L'Hopital's rule here, but he doesn't actually use it in the solution itself. They actually just use the basic techniques of direct substitution and algebraic properties to simplify the limit expression to calculate it. So I'm not going to use the L'Hopital's rule, even though you could possibly use it, but I think it's kind of unnecessary in this case. So basically what they're asking us is to calculate this limit. So there's basically three primary techniques that you use when you're calculating limits. You either directly substitute the limit into your expression, or you use algebraic properties such as canceling out factors or to simplify your expression, or you use the conjugate to get rid of any radicals or any troublesome things in the denominator, basically. So in this limit here, we're going to calculate the limit as x approaches 3 of this expression. Okay, so we were to plug in 3 into here, right? So if you use direct substitution, we would get 9 plus 12 minus 21 divided by 9 minus 9. And that gives us an indeterminate form of 0 over 0. So given this indeterminate form, you could use L'Hopital's rule, which states that the limit of an expression is also of a rational expression is also the same as the limit of the derivatives of each of those expressions in the rational expression. But I don't see that as, I see that as a necessary way of calculating the limit because we can use algebraic techniques to simplify our expression here. Okay, so since it gives us an indeterminate form, we have to simplify our expression first. Okay, so let's write out our limit again. And the thing I'm going to do is I'm going to factor the top and the bottom. So by factoring the top, I find that this is x plus 3 divided times x minus, it's actually x minus 3 times x minus plus 7. Okay. And the bottom, if I factor it, I see there's a difference of squares here, so it's just x plus 3 times x minus 3. You guys can pause the stream or the video to check that these factors are indeed the factors of the numerator and the denominator. So once I find that these factors exist, I can basically cancel out x minus 3 because they are both on the numerator and denominator, and we get that the limit is actually this expression, x plus 7 divided by x plus 3, and we're calculating the limit as x approaches 3. Now we can use direct substitution. If we use direct substitution, we get that the limit of as x approaches 3 is equal to of x plus 7 divided by x plus 3 is equal to 10 divided by 6 or 5 divided by 3. Okay? So that's the limit of this expression. We just simplified it using algebraic techniques. Okay, moving on to the next question. All right. So the next question asks us to find the maximum volume of a rectangular box inscribed in a sphere with radius r. So what it means for a rectangular box to be inscribed in a sphere, if I were to draw out the 2D representation of this, so let's say that our sphere has a radius r like this. Okay. The rectangle is inscribed in a circle is as if the rectangle is touching each of the vertices of the rectangle are touching the circle. That's what it means by the rectangle is inscribed within the circle. Okay, so it kind of looks like this, but in the 3D representation. Okay, so we have to find the maximum volume of the rectangular box. So the strategy involved here is to basically find the volume of the rectangle in terms of the radius and also of the dimensions of the rectangle, and then finding its derivative. And when we find the derivative of this rectangle, we're able to find the dimensions of the rectangle that maximize the volume of this rectangular box, and plugging it back in, we're able to find the volume. Okay, so that's what we're going to do, and this technique is called what we call optimization. Okay. So the first thing to note is that, looking at our 2D diagram here, that the radius of the box, or the radius of the circle, or the diameter of the circle, actually I should say, is also the diameter of the rectangle if it's inscribed in the circle, or the sphere. Okay, so let me draw out the diameter. Sorry for this really crude drawing. It's, okay, maybe I shouldn't use the line. I'll just draw, okay. So, the diameter, okay, let's try this again. The diameter of our rectangle is the same as the diameter of our sphere, okay? So the diameter of the sphere is equal to diameter of the rectangle, okay? And given our handy formula, the diameter of a rectangle, so the dr, is equal to the square root of x squared plus y squared plus z squared, where x, y, and z are the dimensions of the rectangle. Or rectangular box, I should say. Okay, so equating this to the diameter of a sphere, we see here that the square root of x squared plus y squared plus z squared is equal to 2r, or the diameter of a sphere. Okay, so if we square both sides, we get x squared plus y squared plus z squared is equal to 4r squared. Now we're going to obtain the volume of a rectangular box, which is going to be x times y times z. And if we write this expression in terms of z, we get z is equal to the square root of 4r squared minus x squared minus y squared. Now we're going to plug this into our volume equation, and we get the volume of the rectangular box in terms of x, y, and the radius of the circle is xy times the square root of 4r squared minus x squared minus y squared. Okay? So does that make sense so far, I guess? So now that we have a volume formula in terms of x, y, and the radius, we're going to calculate the partial derivatives of our equation here. Okay. So by finding the partial derivatives of our derivative, okay, our partial derivative of our functions here, we're able to basically find the critical points of each of our partial derivatives and equate them into a system of equations. And by equating them to a system of equations, we're able to find the values of x and y that satisfies both equations. And if we are able to do that, then we're able to find the dimensions of x and y that directly that maximize the volume of a rectangular box. Okay, so I'll bring us through it slowly. So when we're calculating partial derivatives, we're going to derive in terms of only one variable, and we're going to keep the other variable constant. Okay, so what that means is that if we're partially deriving in terms of x, for example, then all the y variables are held as constants. Okay, so now we're going to derive this function in terms of x. So I see here that this is a product rule of differentiation. So I'm going to derive our first function x. So it's going to be y times 4r squared minus x squared minus y squared. Okay. And I'm going to derive the second function, which is y times 4r squared minus x squared minus y squared, which is going to equal minus x squared y, yeah, divided by root of 4r squared minus x squared minus y squared. And that's equal to y times 4r squared minus 2x squared minus y squared divided by the root of 4r squared minus x squared minus y squared. So this is the partial derivative in terms of x of our function. And if I were to do the same for our y, we get the partial derivative of y to be x times 4r squared minus 2y squared minus x squared divided by the root of 4r squared minus x squared minus y squared. Okay, so you guys can pause the video and you guys can calculate the partial derivative, but it's basically the same thing as calculating the partial derivative of x. Instead, you're holding x to be constant and you're deriving in terms of y. And you're using the chain rule for the second function, and you're using the product rule of differentiation for the entire function. Okay, so now that we have found our partial derivatives, we're going to set both of these equal to 0. So if you set v of x to be equal to 0, we are going to find the values of x and y that satisfy our vx equal to 0. Okay, but since it's a rational expression, all we need to do is examine the expression in the numerator, because the expression in the numerator dictates when our function is equal to 0. Okay, so we're going to examine y times 4r squared minus 2x squared minus y squared is equal to 0. And the same thing for partial v of y, or partial y of v. We're going to examine just the numerator, which is x times 4r squared minus 2y squared minus x squared equal to 0. And then we're going to equate these in a system of equations and solve for the variables that satisfy both of these equations. Okay, so looking here, we can cancel out y in our partial derivative of x and cancel out x in our partial derivative of y by dividing both sides by x and y. Okay, by doing so, we get this system of equations: 4r squared minus 2x squared minus y squared, and 4r squared minus 2y squared minus x squared equals 0 equals 0. Okay, so I'm going to use the process of elimination instead of substitution to calculate or to compute the system of linear equations here. So the first thing I'm going to do is I'm going to multiply equation 1 by 2. So if I multiply equation 1 by 2, we get 8r squared minus 4x squared minus 2y squared equals 0. And this is 3. And now I'm going to do 3 minus 2 here. So if 3 is minus 2 here, we get 4r squared minus 2y squared minus x squared. 0. And if I subtract this, what we get 4r squared minus 3x squared. Right? Yep. And we also get y squared, 2y squared plus 2y minus 2y squared plus 2y squared is equal to 0. Is equal to 0. Okay. And now we have here that we can solve for x in terms of r, right? So x is going to equal 2r divided by root 3. Okay. So now we have found the value of x that satisfies these equations, and now we're going to plug x back into one of our equations here to solve for y. So we're going to plug x back into 3, and if we plug x into, let's not do into 3, let's do into 1, we get 4r squared minus 2 times 2r divided by root 3 squared minus y squared equals 0. We get that y is equal to 2r root 3. Okay. So now that we have x and y, right, we can now find z. So if we plug back in x and y into our z function here, we get that z is equal to, so z is equal to the root of, whoops, the root of 4r squared minus x squared minus y squared, right? So you plug x and y back into here, we get 4r squared minus 4r 3 squared minus 4r squared 3. And if we calculate this, we get 1284. We get the root of 4r squared 3, or 2r root 3. Okay, so z, x, and y are all equal to 2r root 3. So therefore, the volume that is maximized by these dimensions is going to be equal to volume is equal to x times y times z, which is equal to 2r root 3 cubed, and that's equal to 8r cubed 3 times divided by 3 times root 3. Okay, so in conclusion, we first derived a formula for the volume of our rectangle inscribed within our sphere by first figuring out that the diameter of a rectangle is the same as the diameter of a sphere. By doing that, we're able to express the z dimension of our rectangle as in terms of the radius and x and y. And by doing so, we're able to find a formula for the volume in terms of x and y only. After that, we found the partial derivatives of this formula here, or this function, and then we calculated the critical points for each of these partial derivatives. So these critical points point to the fact that we want to optimize a rectangle to have the maximum volume within our sphere. So when we set our derivative to be equal to 0 for both partial derivatives, we're saying that we want to find the values of x and y the dimensions of x and y that will maximize our volume. So once we find the partial derivatives, we made it into a system of equations to find the values of x and y that satisfy both partial derivatives. And by doing so, we're able to calculate the dimensions of x, y, and z. And it turns out that the dimensions that maximize the volume of a rectangular box within a sphere that is a cube with the dimensions 2r divided by root 3. Okay? So other than that, the solution is correct, and we can move on. All right. So how do you find the domain and range of the function f of x equals 1 over x minus 2? Okay, so in a lot of different lessons, I've described what the domain and range are, but I'll do it again. So for the domain, it is all the values of our number sets that define our function. And what that means it defines our function is that it maps to a legitimate value. It maps to a defined value. So what undefined values are basically like infinity, negative infinity, or like discontinuities, right? So the domain is basically all values of, let's say, x that define our function. So the function is kind of like a bridge that maps our value of x within our domain to what our values in our range. So the values in our range, and I'm going to describe it as f of x, is all the possible values that are mapped from our domain. So the domain and range of a function varies with different kinds of families of functions. In this case, we're given a rational function with a numerator of 1 and a denominator of x minus 2. Okay, so one of the ways that we find a domain is by doing the opposite. We find the values of the function which are undefined, right? And by finding the values of the function that are undefined, we're able to exclude that out of our domain. So that's one way that we find our domain. The other way that we find a domain is by we just graph it and we visually locate all the discontinuities and everything that it does not exist on the function. Finally, the last way is that we can calculate the limits of the function, but that's beyond the scope of this question so far, so we won't cover it. Finally, the range. So the range is closely related to the domain, and the fact that if there are values of the domain that are restricted, that most likely means that the range might also be restricted to that value that's mapped. So one way that we can calculate the range or find the range is by also visually graphing it. But my personal favorite is to calculate the inverse of the function. And by calculating the inverse of the function, and we write notation as f of inverse of f to the power of -1, we basically calculate the domain of our inverse. Okay. So what this means is that if the function maps a value of x to a value of f of x from domain to range, the inverse reverts that. It maps a value from our f of x of our range of our function back to the domain of the original function. So that means that the range of the original function is the domain of the inverse, and that the range of our original function, or the domain of original function, turns to be the range of our inverse. So we're going to use this technique to calculate the range of our function. Okay, now moving along. So first we want to find the domain of our function. Okay, and let me write out our function again. F of x is equal to 1 divided by x minus 2. So, like I said, a very easy technique is to find all the values of x which make our function undefined, and that's very simple. All we need to find is, in this certain family of functions, is we need to make sure that we exclude all the values of x that make our denominator equal to 0. Because when anything is divided by 0, we have an undefined value. Okay, so that means that we want to set x minus 2 to be equal to 0, and that is x equals 2. So therefore, our domain is equal to x belongs to all real values, except x cannot equal to 2, because when x equals to 2, our function is undefined, as you see here. So all other values of x in the real number set is valid, but x equals 2. Okay, now we want to find our range. So this one's really simple. So the easy way that I find the inverse function is first I switch my x variable and my f of x variable. Okay, so x equals 1 over f of x minus 2. Then I isolate for f of x again. So if I'm isolating for f of x, I'm going to move it to the left-hand side by multiplying both sides by f of x minus 2. Then I get rid of x by dividing both sides by x. Okay. And then I get rid of this 2 by adding both sides by 2, and we get 1 plus 2x divided by x. Okay. So now I write this notation here. F of inverse x is equal to 1 plus 2x divided by x. And we calculate the domain of our function here. And similar to this rational function, we see here that our domain of our inverse is equal to x belongs to all real values, except x cannot equal to 0, right? Because when x equals to 0, the denominator is equal to 0. And this equals our range. So our range is equal to y belongs to all real values, except y cannot equal 0. Okay? Cool. So other than that, the solution is correct, and we can move on. Finally, let's talk about our last question of the day, which reads, how do you solve 2x squared minus x minus 6 equals 0 by factoring? Okay, so I covered this multiple times, but I'm going to use the cross multiplication method. Okay, so if you have a quadratic function of standard form ax squared plus bx plus c, you can factor it into form dx plus e times gx plus f, where a is equal to d times g, b is equal to df plus eg, and c is equal to e times f. So d, g is factors of a, e, f are factors of c, And if your b is equal to the sum of the products of these two, d times f and e times g, then you have found your factors. Okay. So in this case here, we're going to find the factors of 2 and 6 and cross multiply them. So let's find the factors of 2. That's either -1 and -2 or 2 and 1. And we're going to do 2 and 1 here. We're going to find the factors of 6. Factors of 6 are 1, 6, or 2 and 3. And there's also a negative sign here. So we're going to be saying -3 and, oops, it should be the other way around. It should be 3 and -2. Okay, so these are the factors of -6, and these are the factors of 2. You guys can pause the videos to check. And now here's where the cross multiplication part comes in. We cross multiply them, so that we're going to have 2 times -2, which is -4, and 3 times 1, which is going to be 3. And if we add those together and we get our middle coefficient, which is equal to b, then we know that these are the factors, 2, 3, and 1 and -2. So therefore, 2x squared minus 6 minus x minus 6 is also equal to 2x plus 3 times x minus 2. So now that we need to solve this this equation here, right? We want to solve for the values of x that makes the equation equal to 0. And that's very easy at this point, right? Because we can just solve the respective terms of each of these to equal to 0. And if they equal to 0, then the whole product equals 0. So we're going to solve 2x plus 3 equals 0 and x minus 2 equals 0. So 2x plus 3 equals 0 is going to be x equals -3 over 2. And for this one, it's going to be x equals 2. So therefore, x equals -3 over 2, and 2 are the solutions. Okay, so that basically wraps up this question. And all I can say about the cross multiplication method is actually it's very easy to employ, but it takes a lot of practice to get used to. So I'd say that if you're in grade 9 or 10, I would say just find as much practice to do with quadratic functions and factoring them, because they are very applicable in higher level mathematics, and save a lot of time and work when you're trying to calculate the factors and solutions. Okay, but other than that, the solution is correct. And okay, cool. So that wraps up today's lesson. I covered 9 questions related to calculus, functions, and algebra. If you have any other issues with your homework or tests or concepts, please submit them from OneClass and we'll get to them as soon as possible. But other than that, I wish you guys a good night. Have a good day. Bye-bye, guys.